Hey, how's it going? I'm Thane Roberts, and here's my presentation for MCN 4008 Finite Element Analysis, Assignment 1. So to start things off, we're going to give a problem overview. The spring constants for stiffness were based on my student ID, and those are 135 kilonewtons per meter, 145 kilonewtons per meter, 170 kilonewtons per meter, 135 kilonewtons per meter, 210 kilonewtons per meter, 215 kilonewtons per meter, and 135 kilonewtons per meter, as well as 145 kilonewtons per meter. Each of the 8 springs can be seen here in the figure. So it goes from left to right in terms of this. So this is our first spring, the 135, and this is our final spring, the 145. The link beam section, A to B, has a universal beam cross section, 150 UB 14, and the material for everything was assumed to be structural steel with a modulus of 200 GPa. This beam is hinged at A and also at C. We also got given a cross-sectional area for the link BC, which you can see here. And as you can see, we also got given some dimensions for the height. So we know that that's 45 degrees, and we know that the length of AB is 1.8 meters. So in modeling this in ANSYS, what we did is we created a beam and link in space claim, and then basically just 2 lines in space claim, and then we gave them cross sections. So for AB, we gave it the universal beam cross section based on what the first thing I came up when I googled this cross section online. I modeled it to be exactly like that. However, for link BC, I had to make an assumption. I assumed that it had a circular cross section, and I assumed that link BC, therefore, because it has a circular cross section, it would have a radius of 7.98 millimeters. The material of absolutely every component was taken to be structural steel, simply for simplicity. In order to add the springs, I created a series of named sections, 0.2 meters along the beam. So along the 1.8 meter long beam, there was a series of 0.2. Every 0.2 meters, I would have a new section, and the named section would be named what the spring's going to be. I used, for the springs, they were placed body to ground, and I basically did a direct attachment on a node for those. As for the supports at A and C, what I did for those is, because we are doing a hinge support, you want to constrain movement in X, Y, Z, but we only want to constrain rotation. We only want rotation to be constrained in the x-axis, and also we would want the rotation to be constrained about the y-axis, and therefore we'd only allow rotation around z. So rotation around z. So imagine like you're going around it. Yeah, when you think about it three-dimensionally, it makes sense. So that's how we get our hinged joints. We did that for A and C. So both supports we used a remote displacement. So I used a remote displacement for both of those. As for the coding, which I used for APDL to include a distributed load from the section AB, what I did is I created what the Q naught is in the term, which is kind of like your maximum load. Also, I based it on basically the mesh size, and I initially had to change this a couple times because I didn't know how big my mesh was going to be because I hadn't done my convergence yet. So when I came back, I did change this code, and I discovered that 72 divisions was that kind of magic number that made it work. Speaking of convergence, what I did is I started with 0.2 meters for the node size, quite large, and then I just kept on halving it and seeing how the directional deformation minimum changed. And as you can see, the directional deformation minimum that I got for pretty much most of these around 6 millimeters. However, the change between the directional deformations, it stopped changing it around here, which meant that this was a good sort of node size to settle on. And as you can see in our graph here, the graphing tool in ANSYS just wasn't willing to cooperate, so I just made something real quick in Excel. Alright, onto the results. As you can see here, we have our maximum deformation at A, around A, near A, I guess you'd say, and it's about 0.7 millimeters in the positive. Wait, no, it's negative, so negative 0.7 millimeters, so still down. And then we also have our minimum, and our minimum is significantly larger. It is around 6 millimeters, so we've got around a 6 millimeter deformation around here. About a meter from A, we have this 6 millimeter deformation. As for our rotation, we got a maximum rotation around point B, and it's around, looks to be about 4.6 millimeters. Whilst our minimum, which happens at A, we got a massive number, around 10 millimeters, so quite a lot of rotation around A. So for a reaction at support A, we got around 59 kilonewtons. You could also find the direction because we've got X, Y, Z coordinate components. You could calculate the exact direction, but just for simplicity of like what is the reaction, it's 59 kilonewtons. For the reaction and moment at support B, which is C, which is the force in link BC. So that link that we saw earlier, BC, this is the force in BC, and as you can see, the force in BC kind of goes at the 45 degrees of BC, and we get around 59 kilonewtons again. As for a moment, we get, looks to be e to the 0.12. I think that's quite a small, relatively small moment that we've got going on relative to some of the other things. If I'm reading that correctly, ooh, who knows. As for our reaction in all the springs, what I did is I used those named sections that I used in my spring placement to put a probe at each of the 8 springs. And from those probes, I got basically compressive forces in each of the springs. And the most compressive force was in spring number 9, K6. So throughout this learning and this problem that we set out to solve, I had to make several assumptions in order to just get the ball rolling. We had to assume that the material properties were the same in every single direction. We had to assume that the supports were basically could be modeled as hinge supports, and we also had to assume, I guess, that all of the components were that structural steel material, which they were said to be. Some of the challenges that I found it quite challenging getting the spring placements right. But after some careful attention and rewatching some video tutorials, I was able to fix that up. I also had some challenges when it came to convergence and the element size. Deciding on how small to make my elements in order to have the, I guess you'd say, the most sort of accurate mesh was quite difficult, but eventually I had to use Excel because the feature wasn't working in Answers for some reason. Maybe it's because of the student version. I ended up making an Excel, and I decided on a pretty good element size for convergence. I learned a lot of lessons. I learned how to set up these type of scenarios in Answers. I learned how to get results in terms of deformations, forces, and also moments. And I also learned how to analyze structures better using Answers tools. Please note while making this recording that I've caught a rather nasty cold, and it has definitely impacted some things in this presentation. I hope you enjoyed hearing all about how I went about solving this intriguing problem.